All right, here we go. This is also Unit 7, Lesson 1, but I wanted to break this up into a Part A and Part B to make it a little more easy to split up here for you today. Part A was going over the second fundamental theorem of calculus, which remember told us how to, as I've written out here, told us how to take the derivative of integrally defined functions. And we learned that if you take the derivative of a definite integral, you can just stick the variable upper limit into your original function, and then don't forget the chain rule here. What we're going to be working on today is answering questions when you have these integrally defined functions and you have graphs that you need to interpret. So there's not going to be a lot of taking antiderivatives today, but it's more going to be like the ones where we did the areas under the curve using geometry, and sometimes you found the slope, and sometimes you found the value. So it's very conceptual and not as much just like exact antiderivatives and things like that. Things to remember: the definite integral represents the area under the curve of a function. Anytime you see this right here, that's literally what it means, the area under f of x from a to b. The first FTC taught us that we can do that using antiderivatives, so it links those two key calculus concepts of area under the curve and the derivative. In the last lesson, we proved the FTC Part 2 using the FTC Part 1. And finally, just remember, these are all things. If you're given a graph of something, I could ask you to calculate the area under the curve, to tell me like what f of 2 is, or to calculate the slope. And usually in the course of a problem, you'll be asked to do all of them. And so let's say, okay, so here we go. This is g of t, and there's a separate function. There is a separate function f of x, which is defined as the definite integral from -4 to 2x of g of t. Woo! Okay, that's a lot, but let's take it one step at a time. First, find the value of f of 0. Okay, that's not bad. That means literally plug in 0 for x. Careful, not for t. So what this says here, if we plug in x, is the definite integral from -4 to 0 of g of t. And so now you can see kind of how these functions work. We start at -4, right? And the value of x, which in this case was 0, well, it tells us how far to paint. And when you plug in 0 here, well, we paint from -4 to -3. I'm labeling that red because it's under the axis. We paint from -3 to -2. That's green because it's above the axis. And just to get some separation here, because I want to make sure we see what's going on, we're going to have this rectangle. It'll also be a positive. And then finally, we're going to have this quarter circle here. And so basically, all this did right now, this was a fancy way of asking us to calculate the area under the curve from -4 to 0. Those two first triangles will cancel out. The blue rectangle will be 2. And then what do we have here? We have a radius of 2. So the whole area, pi times 2 squared would be 4. This is 1/4. So this is just going to be 2 plus pi. So this first one here will just be 2 plus pi. Just had to kind of interpret what was going on. All right. Then we are asked to find the value of f of 2. Okay, well, f of 2 is the definite integral. Okay, this is a little bit pretty much the same thing. If we plug in 2, this is the definite integral from -4 to, it looks like +4 of g of t. And I'm going to use a shortcut here. I'm triple checking this to make sure this sure looks symmetrical. And so since it is symmetrical, I'm just going to assume that this is doubling this to save us some time here. 4 plus 2 pi. Everything there looks like it's doubled. So I just went ahead and did times 2 on that one. All right, now here's where things get tricky. What is the value of f prime of 1? Okay, so I'm not even going to look at the graph yet. I'm just going to make sure I know what f prime is. So f prime of x, if I try and take the derivative of, right, I'm taking the derivative of both sides here. Using the second fundamental theorem, I have g of, plug in 2x, don't forget the chain rule, times 2. And so f prime of 1 would be g of 2. Well, this is a graph of g. So g of 2 looks like it's just 1 times 2. So this would be 1 times 2. This would be 2 here. So this comes from the second FTC, and the rest is just pulling off values there. Likewise, f prime of negative 2 would be equal to g of negative 4 times 2. G of negative 4 looks like it's negative 1 here. Negative 4 comma negative 1. So we're going to have negative 1 times 2 equals negative 2. All right, now finally the last one. You could easily be asked to take a second derivative here, and they might not ask you the first derivative first. You might have to do all of this and realize that what you're being asked to find, if f prime of x is equal to g of 2x times 2, well then f double prime of x is going to be g prime of 2x times 2, chain rule, and probably that's a little bit easier to see if we, in the first case here, clean this up a little bit, move this 2 out front. So 2 times g prime of 2x, chain rule, times 2. So this is actually going to be equal to 4 times g prime of 2x, and that's what the second derivative of x is. And so if we actually do the second derivative of 2 like they want, we'll be finding 4 times g prime of 2 times 2 is 4. All right, well, g prime of 4, this looks like a slope of 1 over 1 there. So this does end up just being 1, right? I'm reading the slope here because g prime, if this is a graph of g, is the slope. And so this answer here would just be 4 times 1, which would be 4. I wanted to leave this as a very short video. The delta math ones, you're just going to have one of each one to do. So feel free, right, like try it, look at an example, message me if you need help. The delta math ones, everything you need is basically contained in what's on the screen now, but they obviously ask it in some tricky ways, and I'm happy to help you with that. Make sure you get through as much of that as you can so you're ready to ask good questions in class on Thursday and be ready for the summative that's due at the end of the week.